let's say that we have a particle that is forced to live between x equals 0 and x equals L, and that it is in a state psi of x and t, which is a weighted superposition of the ground state and the third excited state, or n equals 4, so psi 4 of x where psi n of x is, of course, root 2 over L sine of n pi x over L, and En is n squared h squared over 8mL squared, where m is the mass of the particle. So now let's say that we measure the energy. So we measure the energy of the particle, and just experimentally we find that we will either get E1 or E4, one of the two values of energy in the superposition. And we can imagine doing this many times. Having many systems in exactly that state, and then measuring the energy, and then calculating the average of all those measurements. So let's calculate the average. The expectation value from theory is going to be equal to psi star, or the energy is given by the Hamiltonian operator, and that will give us an integral over all of space, or really 0 to L, because the wave functions are 0 outside of that. So this looks like root 2 over 3 psi 1 of x actually with a positive, because this is psi star, times, we have h acting on psi, and these are eigenfunctions, so we'll just get the eigenvalues, E1 times root 2 over 3 psi 1 of x e to the minus I plus the eigenvalue E4 times 1 over root 3 psi 4 of x e to the minus I E4t over h bar. We integrate this in x. Of course, psi 1 squared, the first two terms multiplied together will give us psi 1 squared. Time-dependent part disappears because there's a plus and a minus here. And so we get 2/3 E1 because these functions are normalized. Sorry, actually, no, that's right. The root 2 over L, I was thinking I needed to be included here, but it's in this function. So the function psi 1 of x is normalized, so psi 1 squared integrated from 0 to L, that is 1, so we'll just get 2/3. We'll just get E1 times 2/3, or 2/3 E1. The cross term, this term times this term, gives us 0 by orthonormality, right? We're integrating over from 0 to L over the entire space. So orthonormality holds. Both cross terms give us 0, and so we have the last term, which is this times this, which will give us 1/3 of E4. So this is the expectation value. It's the average over many such systems on which we perform a measurement of energy that initially are in this state, and this is what it looks like. But now let's again go back to imagining that we measure the energy, and let's say we get E4 after a measurement, and now we measure the energy again, and we continue to get E4. So once we've done a measurement of energy on one system, then we know that the average energy, because the energy is fixed, will continue to be E4. And so we can say that the expectation value of the energy prior to the measurement and post measurement, so prior to and post measurement, is not the same. So is energy conserved during that process?